Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this.
Determination of compass error by azimuth of the sun, practice problem 9. Let's jump right into it. Problem 9. And we have some givens. And what are we given in the problem? We are given the date. Given the date, and that is June 12th. June 12th. And it's all 1981 in these problems. The zone time we're given. Zone time, we're going to say ZT equals 0919. 0919. It's 919. We're given our position, our DR position. DR position is equal to 2652 north. 26 degrees, 52 minutes north. And we're given longitude, which is 84 degrees, 34 minutes west. And we're given the chronometer time. So the chron time. Chron time is 3 hours, 17 minutes. 3 hours, 17 minutes, 0 seconds. And we're given the chron error. The chron error is 1 minute 40 seconds slow. 1 minute 40 seconds. And it is slow, which means we need to add to catch it up. And it gives us, at that time, an azimuth of the sun is obtained. The bearing is 089.5, sun bearing. Sun bearing is equal to 089.5 degrees PSC. And the variation is 4.5. Variation is equal to 4.5 degrees east. And it wants to know, what is the deviation of the standard magnetic compass? It wants to know deviation. What does that equal? So we start by, we need to get GMT. And there's some ambiguity in that chronometer because it's based on 12 hours, like a analog watch. So let's get the approximate GMT. What is the approximate GMT on our ship? And we do that by the zone time, which is equal to 0919. Yeah, 0919 is the zone time. And then we can take our longitude, because we're trying to get to the Greenwich Mean Time, which is at the prime meridian. So our longitude, which is 84 degrees to the west, we divide it by 15. There's 15 degrees in each time zone. So 84 divided by 15 equals 5.6. Equals 5.6. And anything, we always need to round to the first whole number. So that's 6 hours. Do we add or subtract this? We know that by the sign here. It's west. So, but let's draw it out. If we look at, like, this is the prime meridian. So this is Greenwich Mean Time, prime meridian 000. Set up some time zones. If you go to the east, you add to the east. If you go to the west, you subtract to the west. Just like New York to California, from east to west, you subtract time. But we're way over in the west. We need to add to get back to the prime meridian or Greenwich Mean Time. We need to add. So we're going to add these 6 hours. We add 0, 6, 0, 0, 19, and 9 plus 6. So we're looking at 1519. This is the approximate GMT. And we know that we're in the same day. We didn't change days. So this will also be, just to take note, June 12th. It's going to be June 12th. Good. Now, let's take a look at, we need to get our actual GMT. So what is our actual GMT? And that's based on the chronometer. So the cron time is equal to 317.0. 317.0 hours, minutes, seconds. Then we need to account for the cron error, which is equal to 1 minute 40 seconds slow. 1 minute 40 seconds. And it's slow, so we need to add it because we need to catch up. So 40 seconds, that's 18 minutes, 3 hours still. So 3 hours, 18 minutes, 40 seconds. So this 3 hours, if you compare it, that's why we get the approximate GMT on our ship. So we know where we are. Okay, 15 hours. That's 12 hours ahead. And I said there's ambiguity in this because it's based on 12 hours. You'll never see a cron time that's over, like in 13 hours. It's like 1250 something is the highest it'll get. So we add 12 hours. Add 12 hours to this and you get the other side of it, which is 3 plus 12 is 15. So here you get 15 hours, 18 minutes, 40 seconds. Now we're lined up. See that 1519? We're at 1518.40. So this is the actual GMT on June 12th. Good. GMT June 12th. Now that we have GMT, we can get the GHA, or the Greenwich hour angle of the sun. And to start, we start with 15, so get GHA for 15 hours, and then we go to the increments table and we'll get GHA for the increments, which are 18 minutes 40 seconds. So 18 minutes 18 minutes 40 seconds, and we'll get what those equal, and we'll add them up. And then right across from those values is going to be the declination and our D correction. So we'll get those as well. We're set up here to get into the Nautical Almanac. We need June 12th. June 12th. October, August, June 21, June 18, June 15, June 12th. So here's the sun column. June 12th, sun, GMT. So this is our day again, 12. That's right, June 12th. And now we're looking at 15 hours. So we come down, here's the hours, 15 hours. So it's 45, 3.3. 45, 3.3 is the GHA. 45, 3.3. And the declination's right across from it. So again, we're 15 hours, 45. So here's the declination. North 23, 10.2. North 23, 10.2. North 23, 10.2. And we can get our D correction here. See down here is the D, 0.1. Do we add or subtract the 0.1? Let's figure that out. So we're on the 12th for 15, Okay, 45,303. North 23, 10.2. Okay, just double checking. You don't want to get this stuff wrong this early in the problem. And if we go down to the next hour, it's going up 10.4.5. So we add this D correction of 0.1. We add 0.1. So that's the D value. And now we'll go to the increments and corrections, and we'll get the we'll get the increments and corrections here. So we'll flip into the back. Increments and corrections for 18 minutes. 18, 15, 18. So here's 18 minutes in the sun. 18, here's the seconds. 18 minutes, 40 seconds. So we drop all the way to the 40 seconds. We get 4 degrees, 40.0. 4 degrees, 40.0. 4 degrees, 40.0. Okay, and we add that. And now, when we get our D correction, we need that. So there's a column for D correction here, and it's 0.1. We just use 0. Good. So this comes, our declination ends up equaling north 23 degrees, 10.2 minutes. There's our declination. We'll need that. And let's add up our GHA. 43.3, and then 45 is 49. 49 degrees, 43.3 minutes. This is our GHA of the sun. So our Greenwich hour angle of the sun is equal to this, 49 degrees, 43.3. We need to get our local hour angle, our LHA. So in order to do that, we need to account for our longitude. It's west, so we're going to subtract it. So we say minus west longitude of 84.34. 84 degrees, 34.0. 34.0 minutes. Okay, and you can see we can't take 84 out of 49. So what we do is it's a compass. So we just add 360. So we go 360 plus 49 equals minus 84 equals 325. 325 degrees. And then, good, we can take 34 out of there. So let's do 43.3. 43.3 minus 34 equals 9.3. Probably should have done this first to make sure I didn't have to borrow over here, but it worked out. So this is the LHA, the local hour angle of the sun. LHA of the sun is equal to 325 degrees, 9.3 minutes. Cool. Let's throw these up in our table. So our declination is the first part of our table, and it equals, let's just keep going. Declination, dr lat. So our declination, dr lat, and LHA are the values we need. Our declination is north 23. North 23 degrees, 10.2. 10.2 minutes. dr lat, 26. 26 degrees, 52 minutes north. 52 minutes north. LHA is 325. 325 degrees, 9.3 minutes. 9.3 minutes. Okay, with that, we can get some information from these numbers. And our dr lat and Dec have the same name. They're both north. So we can say Dec and dr lat are same. That's important. They're the same. Now let's get our base argument. Base argument. And that just means the degrees, 23, 26, 325. 23 degrees, 26 degrees, 325 degrees. Good. That's our base. Now let's get our base z. We can get those with those base numbers. And z is angle. Let's get the base z. These come from site reduction tables. So we look up the LHA 325. Let's see. Okay, they're going up. 325. Okay, good. So we know we're in the right side of the book because there's 26, which is our base dRlat. That's here. So are we same or contrary? Here's the contrary. Here's the same. So we need to be over here. So we're the same. We're 325 LHA, and our Dec is 23. Declination 23. So we're same, 325, 26 in the Z column down to 23 declination, 87.8. 87.8. 87.8. And now that goes down the whole thing. 87.8. 87.8. Now we need to get our tabulated Z. Tab Z. And what we do for this, so you just knock each one up by one. So like 24, 26, 325, record it here. And then you do 23, 27, 325, record it here. And then 23, 26, 326, and record it here. So let's do that. So our new declination, 24. Let's slide it down to 24 over here. So now we're at same, 325, 26, and the Z column down to 24 declination, 85.9. 85.9. 85.9. And now we're at 2327. So back, make sure we get our declination right, 23. And now we're same, 325, 27 Z column down to 23 Dec. 89.4. 89.4. Last one. So this bumps up to 326. We're going to have to turn the page. There they are. 326, same. And our declination's 23. Like to underline 23 right away. And now we make sure we're same. 326, 26, Z column down to 23 declination, 88.1. 88.1. Okay. And now with our tabulated Z, now we need to find the difference between the tab and the base Z. So we'll find the difference in the Z's. We just punch them into our calculator. Tab minus base equals the difference. 85.9, 85.9 minus 87.8, 87.8 equals negative 1.9. Negative 1.9. And now you get 89.4, 89.4 minus 87.8, 87.8 equals 1.6. And now we get 88.1, 88.1 minus 87.8, 87.8 equals 0.3. Now we have the increments here. We're going to need those. Increments are just the minutes. So 10.2 for the declination, 52.0 for the DRLAT, and 9.3 for the LHA. And now we can get our correction. The way we get our correction is the difference times the increments divided by 60. All right, let's calculate those. So difference times increments divided by 60. Here we go. Negative 1.9 times 10.2 equals divided by 60 equals negative 0.32. Negative 0.32. And now 1.6 times 52 equals divided by 60 equals 1.39. 1.39. And now we get 0.3 times 9.3, 0.3 times 9.3 equals divided by 60 equals 0.04, 0.05 it rounds to. So 0.05. Now we can find the total correction. Total correction by adding all these up. Negative 0.32 plus 1.39 plus 0.05 equals 1.12. So the correction is 1.12. We're just going to round it to 1.1. So here we have the total correction. We're getting there. So the base z equals 87.8. 87.8. The correction applied is positive, and it's 1.1. This is going to give us our z value in quadrantal notation. So we get 0.98. We get 88.9. And now we need to name it. Is it north or south up here? We go by the DRLAT. It's north. So north, 88.9. Now is it east or west? And we figure that out with our LHA. So our LHA is greater than 180, which means it's east. If it were less than 180, it'd be west. In this case, it is east. So to find our ZN, I always like to lay it out, and we can just kind of build a graph that tells us. These formulas are in the site reduction tables as well on the pages, but I always just like to graph it out. So north, south, east, and west. And so our ZN is from north toward the east. It's not past 90, so it's up here. And this is our Z. If you look though, ZN is just Z from north. So it's the same. So Z equals ZN. So our ZN is equal to 88.9. And now we can correct our compass. We can say TVMDC, true variation magnetic deviation compass. When you're going down, you add west. So our true now is 88.9. 88.9 degrees true. Variation was given 4.5 east, 4.5 east. So when we're going down, we subtract east. So 88.9, 88.9 minus 4.5 equals 84.4, 84.4. And now our compass was given 89.5. 89.5 degrees PSC was given in the problem. So from 84 to 89, we're adding. It must be west because we are adding. Going down. So 84.4 minus 89.5 equals 5.1. 5.1 degrees west deviation is what we have calculated. Let's check the problem. Hey, look at that. We get a 5.2. That's really close. Nothing else is close except for this one, but it's east. So 5.2 west is the correct answer for determination of compass error by azimuth of the sun, practice problem 9.